Assalamu alaikum. Hope you are fine. So this is week 14, lecture 1. So in previous cases, we studied the Laplace transform. These were the topics we covered in previous week. We studied what is Laplace transform, okay? And we studied about its basic definition, that what Laplace transform do, that if you have f of t and you apply Laplace over this, you will get f of s, okay? And when you apply inverse Laplace, okay, then you get f of t. So first we studied how we can go from time domain to s domain, okay? Then there were certain properties of this Laplace transform, okay? We studied those properties in detail. We tried to derive those properties, okay? And then I show you some table of different properties of Laplace transform, which really help us getting Laplace transform of many functions. Okay, then what we did, we studied the initial value theorem, IVT, initial value theorem, and then we studied the final value theorem, FVT. Okay, and this is V, okay? And then we studied about inverse Laplace, okay? For inverse Laplace, we did partial fraction, okay? So these were the topics we covered in week 13, which was chapter number 13 of your textbook, okay? Now we're moving further and try to apply the Laplace transform to circuit analysis. Okay, so this is your chapter 14 of your textbook, application of Laplace transform to electrical circuits. Okay, application, it could be applied to any many fields. Okay, but here we are only interested in circuit analysis. So application of Laplace transform to circuit analysis. So how we can apply Laplace transform to circuit analysis and how it can help us. Okay, so we can go and study a little bit motivation behind application of Laplace transform. Okay, so let's say you are given a circuit. Okay, say your circuit is this one. It consists of one resistor, okay, and one inductor, okay, and it is applied with certain voltage, say V of t, okay, and we are interested to find its equation. So this V of t, say the current flow here is, say this is I of t, okay. So if we try to solve this Laplace transform, try to solve this circuit, how we can solve this circuit in time domain, that would be we go back to our circuit analysis techniques. Okay, so in our circuit analysis techniques, we studied how can you find a solution to this. This will contain an equation, a differential equation basically. So it will contain differentials of certain of current. Okay, so if I write equation for this, this will be V of t equal to L di t by dt plus R I of t. Okay, and my goal here is to find the I of t. Okay, so this is simple differential equation. You can solve it by solving this differential equation. Okay, so how you can solve this differential equation? Okay, so we will apply differential ordinary differential equations techniques over here. Okay, this is first order differential equation. Okay, so we can easily find out the complementary solution as well as particular solution of this one. Okay, so first I'll solve the complementary solution. Okay, complementary solution CS. So for complementary solution, what we do that we switch off the force response, we make this term 0. Okay, and then find I of t from this equation. Okay, if you make this thing 0, you will get this equation L di of t by dt. Okay, plus R I of t equal to say 0. Okay, remember you are given this value, this is u of t. Okay, so this is your input is just a step input. Okay, now you need to solve this to find out I of t. Okay, and when you find I of t from this equation, this will be complementary solution. So we put instead of I, we put here just IC. Okay, this will be your complementary solution if you solve this. Okay, so we can solve this by applying differential equation techniques. Okay, so we can write this way. This will be R I of t, okay, dt, and you can divide this side by L and this side by L as well. Okay, so you will get this here L and you will cancel this L. Okay, so we move from this step to this step. Moving further, you get finally on one side you get d I of t. Okay, on the other side you get R by L. Okay, but here you can this contain this I of t into dt. Okay, so we take this I of t here. Okay, so this will be 1 by I of t into dt is equal to R by L dt. Now what we can do to find I of t, we simply take integral to both sides. Okay, so you apply integral, you will get here natural log of I of t. Okay, and here you will get R by L into t. And you remember when you solve integral, you put here integrational constant c. Okay, now this is a natural log, but we just need I of t. Okay, IC of t actually. Okay, so you remember we are getting complementary solution over here. Okay, so we can apply exponential to solve this. You can easily take exponential of natural log IC of t. And here as well you get R by L into t and plus EC, so we can write it EC. Okay, and natural log and exponential cancel each other. You will get IC of t here, and you will get I'll put here Kc for this constant. This will be a constant value, right? So this is Kc e raised to a power R by L into t. Remember this was minus. Okay, you go from right side left side to right side. Okay, so this is minus over here, minus over here, so minus over here and minus over here. Okay, this is your complementary solution. Okay, now you need to find particular solution, and your final answer will be I of t is equal to IC of t, which is your complementary solution, plus I P of t. Okay, so we already find this component. We need to find this component now. Okay, so we will get to the solution. So for for particular solution, we know that our input is constant value. Okay, this is u of t. Okay, this will be 1 and this will goes till infinity, and it will not change its value. So this is a constant. Okay, so you know the rule for finding particular value when your force response is a constant value. Okay, so we can simply say that let's say your particular solution is constant IP of t. Okay, let's say your particular solution is IP of t is equal to, say this is a constant kp. This will be a constant. Okay, now you take this value and put it into original equation, which is v of t, vs of t. Okay, vs denote the source input voltage. This is L di by dt plus r I of t. Okay, you put this particular solution over here. Okay, so vs of t was 1, you already know that. Okay, and here this is a constant. When you take derivative of a constant, this kp, this will end 0 plus r times kp. Okay, now what is kp? Kp will be 1 by r. Okay, now you get the particular solution as well. Now what will be the final answer? This was I of t is equal to IC of t, yeah, plus IP of t. Okay, so you already know what is IC of t. IC of t was Kc e raised to a power minus r by L times t plus 1 by r. Okay, so this is your final answer, and you can multiply it with u of t, because why we multiply it with u of t? Because we are taking just a positive value, that is we are starting from 0 to infinity. Okay, so this is your solution, and these were different steps we followed. So you see it was little bit cumbersome for solving differential equations. Okay, so for differential solving this kind of differential equation, first we needed to find the complementary solution, then particular solution, then we add those two solutions to get the final value of our output, which was I of t. Okay, now let's try the Laplace transform. Okay, let's try using Laplace transform. That whole Laplace transform gonna help us solving such type of equations. Okay, so this was your time domain equation, which is v of t is equal to L L di by dt. Okay, and plus r I of t. Okay, so for this you know what was v of t. Remember that at time 0 I'm considering that I of 0 is equal to 0. Okay, this we will use this term later on. Okay, just remember here that I'm taking I of 0 equal to 0. Okay, so if you transform this equation into Laplace transform, what you're gonna get, you will get v of s. This will be ls I of s. Okay, plus r I of s, right? So you see we transform the differential equation into simple algebraic equation. You can easily find out the value of I of s from here. Okay, you take I of s common, this will give you ls plus r. Okay, and here this is v of s. Okay, you know that this was u of t, so this will be 1 by s. Okay, but let's go this way. So I of s will be v of s over ls plus r. Okay, so this is your I of s. Okay, and you know that what was v of s? This was u of t, and u of t Laplace transform is 1 by s, so we can write the final value as 1 by s into ls plus r. Okay, this is your I of s, but we don't need this, we need I of t. So for I of t, what we can do is simply we can do partial fraction, which we learned in chapter 13. Okay, in previous lectures, you already know that we can do partial fraction of this one, and we can convert it into this form, that is A by S plus 1 by Ls plus R. Okay, you do little bit modification over here, that is you take L common, okay, so that you get the standard form. So if you take L common, this will be 1 by L divided by S into S plus R by L. Okay, and then do the rest of the story for partial fraction. Okay, so this will be B by A by S when you do partial fraction of this thing, and then plus B by S plus R by L. Now you need to find the values of A and B. Okay, so I already found the value of A and B. Okay, so if you put the values of A and B over here, you will get 1 by, value of A is 1 by R actually. Okay, and value of B is minus 1 by R into S plus R by L. Okay, so A is 1 by R and B is minus 1 by R. Okay, you can do partial fraction. So I get this equation in the end. Okay, this is after doing the partial fraction. So I of S is equal to this thing. Now we know that 1 by R is a constant. So 1 by S is what? U of t, right? When you do perform the inverse Laplace. So just you need to perform the inverse Laplace and I of S. Okay, so you will do this rest over here as well. 1 by R by S. 1 by R is a constant, okay, and 1 by R by S plus R by L. Okay, so you apply this inverse Laplace. When you apply it to this one, you will get 1 by R U of t, okay, minus the second one will be 1 by R e raised to power minus R by L times t. Okay, and because the system is defined only for positive value, we apply the U of t. Okay, you can also write it this way: 1 by R minus 1 by R e raised to power minus R by L times t. Okay, now look closely to this equation and compare it with the previous equation which we derived using the solving the differential equation. Okay, so this is almost the same. Here we are getting minus sign. I don't know why. Okay, so there also this was minus. Okay, this term is minus. Okay, minus, this is minus 1 by R. Okay, so we got our solution, that is your I of t. Okay, this is your I of t. So see, we did not needed the differential equations. Okay, we first transform our differential equation into simple algebraic equation, and then we proceed then we use the inverse Laplace, and we got our solution. So this Laplace transform did the trick that we can avoid solving differential equations. Okay, so this is the motivation behind Laplace transform. Okay, we go a little bit further and let's say develop our concepts of different circuits for Laplace transform. Okay, so you know that if you are given a capacitor, okay, and you need to find the voltage across that capacitor, then how you find the voltage across that capacitor? That voltage across capacitor will be in time domain. This will be V of t is equal to 1 by C integral, say, I of x dx, and x we integrate it from 0 to t. Okay, So this is our equation for voltage across capacitor. Okay, and if the capacitor is initially charged, okay, to certain level, okay, so we are starting our integral from 0 to t, okay, so at exactly equal to 0, the voltage across capacitor will be V of 0. Okay, this is in time domain. The same way, say this is equation 1. This is equation for voltage across capacitor. And if you are interested in finding current across capacitor, then this is C dV of t by dt. Okay, and this is equation number 2. Okay, so let's find out the Laplace transform equation for voltage across capacitor. If you are given this equation, you can easily find out the Laplace transform equation for this equation number 1. Okay, so this will be V of s is equal to, you know that integral Laplace transform of this integral is 1 by s, right? So this is 1 by s c, okay, and current is I of s. So this will be I of s, and plus V of 0, okay, its coefficient is 1, so 1 Laplace transform will be 1 by s. Okay, so this is the Laplace equivalent to V of t. Okay, the same way we can find Laplace transform for this current as well. So I of t become I of s. Okay, and this will be derivative become s V of s. Okay, and we are finding what the current, right? So we can also write here another term which will be C V of 0. That is, maybe capacitor was initially charged, maybe it was delivering certain current, so this will be equal to this thing. Okay, so this is the current equation for capacitor, and this is the voltage equation for capacitor. So say this is equation 3 and say this is equation 4. Remember these equations, we're going to use these equations. Okay, the same way, if we can find the same way we can find the voltage and current relation in time domain across inductor. That will be V of t, and we are finding it across inductor, so you can put VL over here. Okay, L over here. So this will be L di of t by dt. Okay, this is voltage equation, and this will be your current equation. I of t is equal to 1 by L integral from 0 to t V of x dx. Okay, and plus if the inductor was initially charged, so this will be your I of 0. Okay, these are the time domain equations. Say this is equation number 5, say this is equation 6. Okay, we're going to use these equations later, and their Laplace equivalent will be this will be V of s is equal to s L I of s, okay, or minus L I of 0. Okay, and this will be I of s equal to V of s over SL, okay, plus I of 0 over s. Say this is equation 7 and say this is equation 8. You just need to remember this equation 7, 8 and 3 and 4. Okay, so let's apply these two circuits. Okay, let's draw a table for circuits. Okay, let's say you have in time domain, I'll say this is time domain. Okay, and say this is S domain, the Laplace transform domain. Okay, so in time domain, if you are given simple resistor, okay, say this is R, here this is I of t, and here applied voltage is, say, V of t. Okay, so S domain equivalent of this will be the same R. Okay, the current become I of S and the applied voltage become V of S. Remember that this circuits and this circuits contain the same amount of information. Okay, now for capacitor, say you are given capacitor and in time domain, and this is your time domain current across this capacitor, and this is the applied voltage in time domain, and this is capacitor value C. Okay, so equivalent in S domain will be, you can use the equations we just derived in equation 3 and 4. Okay, so we can simply make this equation, transform this equation into circuit. Okay, so that's what I'm going to do. Okay, so this is nothing but capacitor, okay, in series with voltage. Okay, this is your I of S. Okay, this is your V of S. This is 1 by SC, and this is V of 0 over S. Okay, and this will be plus minus. Okay, also for equation 4 we can this is your equation 4, so we can also write this into draw this diagram into current sources as well. Okay, we just replace this voltage into current source. Okay, so this will become capacitor, okay, the same I of S plus minus V of S. This is your 1 by SC, and in parallel we inject a current source whose value will be C V of 0. Okay, this is nothing but this equation 3 and 4. This is your equation 3 and this is your equation 4. Okay, this is equivalent circuits for when you have a capacitor in your circuit. Okay, the third is our inductive circuit. So for inductor circuit, again, this is time, this is S domain. So in time domain you have this inductor, here you have this current flowing through that inductor, and this is your V of t. Okay, in S domain again we can use our equation which we derived previously, equation 7 and equation 8, this equation, okay, and this equation. So you can draw this equation circuit diagram, and you can draw circuit diagram for this equation as well. Okay, so for equation 7 your circuit diagram will look like this. You have an inductor and you have a source of voltage whose value is L I of 0. Okay, and this is your LS, yeah, RSL. This is your IS. Okay, and this is your V of S. Okay, the same way for equation number 8 we are transforming this voltage source into current source. Okay, nothing else going to change, so we put parallel a current source. Okay, this is your inductor SL, and here we put a current source, but whose direction will be opposite to the capacitor. Okay, so this will be I of 0 by S. Okay, here you have your I of S, and here you have your V of S. Okay, so look closely. This is your equation 8. This is your equation 8. Okay, and you see why I put this sign opposite to this one, because here we have minus and here we have plus. Okay, so these are circuits equivalent in time domain and frequency domain, that is S domain. Okay, so that's it for circuits. Okay, now we move further and try to solve different equations. different problems using Laplace transform. Okay, so let's say we are given a circuit containing different components. Say we are given this circuit. Remember that this chapter name is application of Laplace transform to circuit analysis. Okay, so we're gonna analyze our circuit. Okay, we will find voltage at different across different component. We will find current across different component. We will find energy consumption across different component. Okay, but using Laplace transform, that is in S domain, we're going to solve our equation, and we will then apply inverse Laplace transform to get our output in time domain. Okay, so let's say you are given this circuit. Here this is R and its value is 10 K ohm. Okay, and here you have given a capacitor whose value is 2 microfarad. Okay, and your input is a current source, that is I of t is equal to 3 e raised to the power minus t and u of t. Okay, so u of t means that there is no previous value. That is, if you find u of 0, this will be 0 because initially the capacitor is uncharged. Okay, so that condition which I told you, that v of 0 or I of 0 is 0 over here. Okay, that is v of 0 is 0 and I of 0 is equal to 0. Okay, and this is your I of t. Okay, so now we need to solve this equation, this circuit, but using Laplace transform. And what we need to find? We need to find the voltage across this capacitor. Okay, we call that V out of t. So you need to find V out of t. Okay, but not in time domain. You will need to find the solution in frequency domain, that is in S domain, and then we will transform that output of V out of S into V of t. Okay, so first what we need to do is we need to find the Laplace equivalent of this circuit. Okay, so the Laplace equivalent of this circuit will be your current source over here. Okay, this is your resistor, so nothing going to change with resistor. This will be 10K. Okay, and for capacitor, this become 1 by CS. You already know that, right? And this is your input, so this become I of S, and I of S will be, this is 3 into e raised to the power minus t. Okay, so when you find the solution to this one, this will be e raised to the power minus t is equal to 1 by S plus 1. Okay, so this become 3 by S plus 1. Okay, you can put C value over here, so you will get the total reactance of this capacitor in S domain. Okay, you already have R, and then this current will be I of S, and what you need to find is voltage across this capacitor, that will be V out of S. So how you can find this voltage across this capacitor? Okay, so first you need to take these things parallel. Okay, so if you take R parallel with 1 by CS, okay, and then multiply that with I of S, okay, you will get V out of S, right? So that's what you need to do. And what is your I of S? I of S is equal to 3 by S plus 1. Okay, so now you just need to find R parallel with 1 by CS. Okay, and this will equal to 1 by C over S plus 1 by RC. Okay, or into I of S. Okay, this is your final equation. You already know what is the value of C. You already know what is the value of R. Okay, you already know what is the value of I of S. Okay, so now we just need to put value of C, R, and IS into this equation, and we will get our output V out of S. Okay, so or 1 by C. C is how much? C is 2 microfarad. Okay, so 1 by we can find out. So your final answer will be this will be 40,000. Okay, you just need to put value of CR in the previous equation. Okay, and this become 1 by RC becomes 4. Okay, and multiply by I of S. So I of S is and remember this is a milliampere. Okay, this is milliampere. So this will be 3 into 10 raised to the power minus 3 over S plus 1. Okay, this is your V out of S. You just need to put values of C, R and I of S into this equation. You will get this equation. Okay, now find, you just need to multiply these equations together. Okay, so if I multiply this thing with this thing, you will get I think so 312 120 divided by S plus 4 into S plus 1. Okay, this is V out of S. This is your desired result, but in S domain. And what we need to find? We need to find the result in time domain. That is, we needed to find V of t, because our circuit given was in time domain, so we need to find V of t. So what can we do here? We can simply use a partial fraction and find the values of a and b. So this become a divided by s plus 4 and plus b divided by s plus 1. Okay, so you need to find the values of a and b. Okay, so if you find the values of a and b, I think so I already found these values. These values become I lost that page, I don't know. Okay, so the value of a will be a equal to minus 40 and b become plus 40. Okay, you just need to find a and b value using partial fraction. Okay, so I already found these values. You put these values over here. Okay, and then 1 by s plus 4 inverse Laplace will be e raised to the power minus 4t. Okay, so this will be 4t e raised to the power minus t minus 4t e raised to the power minus 4t. Okay, and I will multiply this with u of t because I'm taking this positive value, and this will be your v of t. See what we did? We simply applied the Laplace transform techniques and find out the result. Okay, you could use the time domain solution as well, but that is quite complex. Okay, you will need to solve differential equation. If you don't have any idea of solving differential equations, okay, then you can simply apply the Laplace transform. That is the beauty of Laplace transform, that it will transform your differential equation into simple algebraic equation. You will find the solution of that algebraic equation. Okay, and then we'll do the inverse Laplace transformation to get the final result. Okay, so this is a volt. Okay, volt its unit. So this is the simple example. We apply the Laplace transform to our circuit. Okay, now that you have understood the concepts of Laplace transform, we can go a little bit further. Remember that in this example, we consider that our capacitor was initially discharged, that is I of 0, and V of 0, which I took was 0. Okay, now let's say we take another example. Okay, and this time we don't take I of 0 and V of 0 to 0. Instead, that must have some values as well. Okay, so let's say we are given a function, a circuit. Say this is our circuit. This is example from your textbook. Okay, you can go through your textbook, you will find this example over there. You have a resistor R1, you have a capacitor whose initial value is 0, V1 of 0, and this is your C1. Then you have another capacitor, then you have another inductor over here, and you have another inductor over here. This is L1, this is L2, okay, this is C2, and this is minus plus, this is V2 up 0, and here as well this is I1 up 0, okay, and this is here current I2 up 0, and here you have a resistor R2, and you have another source, say this is minus plus VB, okay, VB up T, and this is VA up T, okay. That's it. You have given these circuits, and what you need to do is to find the to apply a mesh analysis technique, okay, to the Laplace equivalent of this circuit. Okay, so first you need to find the Laplace equivalent of this circuit, okay, and then you need to apply the mesh analysis to find the equation of mesh currents, okay, mesh voltages actually. So what we can do, we simply transform this whole circuit into Laplace transform equivalent, okay. From time domain we will go to the S domain, and you already know the drill, how you can go from S domain, from T domain to S domain, okay. But here you are given I1 up 0, I2 up 0, V2 up 0, V1 up 0. How you gonna incorporate these things, okay. So as I derived for inductor previously, you're gonna need these things, okay. And the other one as well, for capacitor as well, okay. So it means I told you before that you need to remember the equation 3, equation 4, equation 3, equation 4, and equation 7, and equation 8, okay. So this is your equation 3, equation 4, equation 7, equation 8. You're going to need this to find the Laplace equivalent of this circuit, okay. So let's try and find the Laplace equivalent of this circuit, okay. So this source will be, I'll start from here, okay. This will be plus minus VA of S, okay. Then this will be R1, nothing's gonna change with R, okay. Then you have a capacitor here, okay. This become 1 by SC, this is reactance of this capacitor, okay. And then in series with this one you have a voltage source. That value will be, this is V1 up 0 in time domain, in frequency domain, that is in S domain, this will be V1 up S by what? S, okay. Then I'll come across this capacitor. This will be your capacitor, and its reactance will be 1 by CS, but C is what? C2, okay. And in parallel with this you were given this voltage, okay. So polarity will remain that voltage polarity, okay. This will be V2 up 0 divided by what? S, okay. Then you have this inductor, okay. So I'll draw this inductor. This will be L1 up S, its total reactance will be this much, okay. And this will be in parallel with voltage source L1 I up 0, okay. And I'll connect this with this one, okay. So this loop is complete. Now I'll switch to this loop, okay. So here you start, you have inductor, its value will be L2S, and you have current across this one as well. This is I2 up 0, so you will need in series a voltage source, that is a plus minus L2 I2 up 0, okay. And then you have the resistor R2, and then you have that voltage source, that is minus plus VB up S, okay. And then you need to connect these together, okay. So this is your Laplace equivalent circuit of this time domain circuit. Now what you need to do is simply apply mesh analysis. you find value equation for this mesh, and you need to find equation for this loop, that is I2 of S. Okay, so it's easy now, right? You will start from here, okay, and then you will this will give you one equation, this will give you another equation. Okay, so I'll step I'll just apply mesh analysis and find the final two equations. Okay, so we will start by we have in loop R1 one by another reactance C1, another reactance C2, and another reactance for L1. Okay, and this whole will be multiplied with I1 up S. Okay, this is what I did. I took I1 multiplied by this thing, I1 multiplied by this, I1 multiplied by this, I1 multiplied by this. Okay, then minus I2 up S multiplied by this and multiply by this. Okay, so this will be 1 by SC2 and plus 1 by plus SL1, okay, into I2 up S, and this whole thing will be equal to what? The applied voltages. Okay, now you have different sources, this source, this source, this source, and this source. Okay, so this will be I'm going to the other side of the equation, that is to the right side. So here I'll use the positive sign convention for this source. Okay, so if this is positive, so I'm going from this to this one, so this will be negative, this will be negative, this will be positive. Okay, so this is VA up S minus V1 up 0 by S minus V2 up 0 by S and minus L1 I1 up 0. Okay, so this is the equation for this loop. Say this is equation 1. Okay, and for second loop you already know how to find for this one, so I'll start from this end, I'll proceed this way. Okay, so this is this will be 1 by SC2 plus SL1 plus SL2 plus R2, okay, into I2 up S, okay, minus 1 by SC2 plus SL1 times I1 is equal to add the different voltage sources. Okay, so this will be VB up S plus L1 I1 up 0 minus V2 up 0 by S minus L2 I2 up 0. Okay, this is your second MS equation. Okay, so if you know different component, what are you interested in? If you need to find out I1 and I2, you have two equations, you have two unknown. Okay, the rest of VA, these things will be known to you. Okay, so you can easily find out I1 and I2 from these two equations, equation 1 and equation 2. Okay, once you find I2 up S and I1 up S, you can easily transform into I1 up T and I2 up T. And once you got the I1 up T and I2 up T, you can easily find out voltage across this capacitor, you can easily find out voltage across this inductor, you can find voltage across this resistor, this inductor, you can find out the losses across this resistor, you can find out the losses across this resistor, and so on. Okay, so total energy consumed across this resistor, total energy consumed across this resistor, you can easily find out those values. Once you know the current and voltage across, you just need to find out the current across this or voltage across this component. Okay, so see how this help us transform this equation. But if you find out that the time domain equation for this one, this will be a headache for you because it involves the capacitors and inductors. Okay, so you will get the second order differential equation. So first order differential equation, for solution of first order differential equation, you needed to find complementary solution, then particular solution. When you get the second order equation, then it's gonna be complex, okay, for you. So better use the Laplace transform. Okay, so you can easily find out your desired output, whatever you are interested in. Okay, so this is what you can do with Laplace transform. That is, you can apply your Laplace transform to find solutions, to analyze your circuits. Okay, uh, and it will help you a lot by transforming your differential equations into simple algebraic equations. Okay, so this is one example. uh, I just use the mesh analysis. Okay, you can try and solve this this circuit by applying nodal analysis. You just need to find node equations. Okay, so I think so you already know nodal analysis. You can easily find out solution to this problem. Okay, you just need to find the equation. Okay, you don't need to find anything else. So that's it for week 13, week 14 actually. And uh, further in this chapter number 14, you have another topic called the transfer function. The transfer function. Okay, so I think so I already gave you the idea of transfer function, that how you can find transfer function of a given circuit. Okay, I'll just revise a little bit. That let's say you have this circuit, say it contains a resistor and an inductor. Okay, and this is applied voltage, and here you have applied the current. Okay, so this is R, this is L. Okay, and we are interested to find voltage across this resistor. This is our output voltage. We are interested in this thing. Okay, so what is transfer function for this thing? Okay, so transfer function is nothing but I told you that this is your output divided by your input. Your input here could be your voltage. Okay, your output could be V of t, your output could be I of t, but I define this V of t. Okay, so your input could be V of t, your input could be I of t. Okay, so if your I of t is your input, then you find this value I of t. Okay, but these are in time domain. You need to find these values in S domain. Okay, so this will look like your output, that is V of S, over your input voltage, that is V of S. Okay, and over here this is your transfer function. Okay, so how you can find voltage across this R? You just need to find I. Okay, and for I you need to find out I. So first let's say transform this into S domain. Okay, so the S domain equivalent of this circuit will be R, this will be LS, this will be IS, this will be your output V of S, this is your applied voltage Vn of S. Okay, I'll say I over here. Okay, now we need to find the transfer function for this. Okay, so for transfer function you need to find your input. Say my input is say I of S. Okay, so what will be I of S? I of S will be nothing but this will be V I of S over R plus LS. Okay, once I get I of S, I can easily find out V of S, which will be multiplication of I of S with R. Okay, so this you will get, you just put I of S, this value, and this will be I of S over R plus Ls, okay, into R. Okay, and this is your output, right? So your output divided by this input, this will be V out of S over Vn of S is equal to R by L. I'll write it this way, and this will be S plus R by L. This is your transfer function. Okay, this is what multiply with your input gives you your desired output. So we call this transfer function. Okay, and I told you before that your transfer function could be simple poles. Okay, this could be a combination of simple poles and zeros. There might be poles at origin. Okay, there might be zeros at origin. There might be complex pole. There might be complex zeros. Okay, so you already have the concepts of those complex and zero pole. Okay, so S-plane I already explained it into previous lectures. Okay, this is how your S-plane look like. Okay, your S is actually a complex number whose values is sigma plus j omega. So here this is your j omega axis and this is your sigma axis. This is your real axis and this is your imaginary axis. Okay, and I told you before in previous lecture that your pole is denoted by this cross. Okay, and zeros are denoted by just zero sign. Okay, so your zeros or pole could be on this line. Okay, that is real. This could be complex if zeros or poles lie over here. This could be just imaginary if they are lying over here. Okay, and if your pole or zero is lying at this origin, we said that poles or zeros are at origin. Okay, there could be one pole at one point. There could be multiple poles at one point. Okay, so that we call repetition in poles. Okay, so this is the end of chapter 14. So what we learned in chapter 14, the application of Laplace transform to circuit analysis. Okay, first we did a simple example. We tried to solve a simple circuit using time domain. Okay, equation that was consist of solving a differential equation. Okay, so in time domain, for solution in time domain, for solution are finding out our output, that is say output is our y of t. Okay, we need to solve differential equations. Okay, while in S domain, when we transform this y of t into y of s, so this is our output y of s. Okay, and for this we will simply need to solve simple algebraic equation, and which we see in this lecture that it greatly help us solving or analyzing our circuits. Okay, because simple algebraic equation solution is very easy. Okay, but finding out solution for differential equation a little bit complex. Okay, so that's it for lecture 14. Okay, and next lecture, that is your textbook chapter 15, we're gonna study Laplace transform, the Fourier transform, okay, and Fourier series. We'll not go to the depth, but we will try to learn the basics of this Fourier transform and Fourier series, okay, and that will be our last chapter to cover, okay. By the end of this week, I'll send you an assignment from chapter number 13 and chapter number 14. Okay, and you will need to submit those assignments by the deadline given. Okay, that's it from today's lecture, and if you have any questions, feel free to contact me anytime, but try to post your questions in MS Teams because everyone could see those questions, and it will be easy. There will be no repetition of same questions. Okay, so thank you for your time.